All right, it's time, so let's get started. Just a quick review of where we are at this point. So we are discussing under what conditions we can learn. In other words, the test error is small, right? When we train a nice model, use it in reality, is the model good or not? And we saw that if the hypothesis set is finite, then it's easy. We use a union bound. But then when the hypothesis is infinite, then we have to go to an effective number of hypotheses, right? Instead of just the number of hypotheses in the hypothesis set. So first of all, we have this effective number of hypotheses given the data set D that we have for training. This effective number of hypotheses, we define it as just how many possible binary vectors this hypothesis set can generate, right? That's represented by the top there, the H with the set of data points as input parameter. So this binary vector, just because we use -1 and 1, which is also called a dichotomy vector instead of binary vector, right? But essentially, that's what it means. How many binary vectors you can generate out of this set of hypotheses, right? And of course, we know that given n data points, the maximum number of binary vectors will be 2 to the nth power, right? No matter how many hypotheses you have. You can have infinitely many hypotheses, but at most you can generate 2 to the nth power number of binary vectors. Yeah? So at most, the effective number of hypotheses is upper bounded by 2 to the nth power. Right? Again, you don't have to copy this. If this is in the notes from last week. Nothing is new there, really. Yeah? But we don't like the first definition because it really depends on the location of those data points, D, right? So we say, well, let's consider the worst case. Yeah, the maximum of those number of binary vectors over all possible choices of these data points. Yeah, because we cannot control what kind of training data points we get, right? So we have to pick the worst case, the maximum. Yeah, and then that is the effective number of hypotheses. Yeah, and we're going to use this instead of the M, the exact number of hypotheses, plug into our Hoeffding bound and so on to generate the upper bound for the test error, right? And this effective number hypothesis, this M, is also called a growth function, right? Because it is a function of n, where n is the number of data points we have in the training data set, right? So this thing actually is an increasing function of n. Yeah? What we want to know is how fast can it grow. We know that there's upper bound, obviously, right? 2 to the nth power is the total number of binary vectors possible. Yeah? But that growth will be too fast, right? It's an exponential growth. And if you plug this exponential growth into our Hoeffding bound, it does not help you. Yeah? It does not give you a useful bound anyway. The growth will be too fast, right? So therefore, we have this question, how fast can this effective number hypothesis grow? Is it really as bad as 2 to the nth power, right? And fortunately, we found out that in many cases, no. We can define a VC dimension to say under what n values it is 2 to the n is exponential. But turns out if n is larger and larger and larger, this m does not grow as exponential anymore. It's limited by the VC dimension. VC dimension is the last value of n, last value of n such that it is 2 to the nth power, yeah, exponential growth, right? After this VC dimension value, if you have more data points, then this thing is upper bounded by this, yeah, by a polynomial function of n, yeah, which is very nice, right? It's upper bounded by this polynomial of n, and the order of polynomial is just the VC dimension. Yeah? Okay. So once we have a upper bound for this effective number hypothesis, again, we substitute into our previous analysis. We have this somewhat funny looking bound, right? But essentially, it's very similar to the union bound that we have before. Yeah, we replace this m by by this growth function, this effective number of hypotheses, right, instead of the actual number of hypotheses. And then there is some adjustment, there are some constants that you have to adjust to get the bound to be correct, yeah, based on the analysis, right? And then we further substitute this bound of the growth function here, yeah, so that it is a polynomial, yeah, in terms of m, with a exponent being the VC dimension, right? This is where we are at from last week, yeah. Okay. Any questions so far about where we are at from last week? Any questions at all? Okay. So the main idea really just to find an effective number of hypotheses, yeah, rather than infinitely many hypotheses. Then you cannot deal with that, right? And then unfortunately, VC, those two very smart people, prove that this effective number hypothesis does not grow exponentially. It grows, in fact, rather in a polynomial, right? If the VC dimension is finite, yeah, it is not infinite. Okay. So therefore, we can say a bit more about this. Yeah. So today, with the lectures, there are two halves. The first half, we'll just wrap up this part about the VC dimension and the implication of it. And then in the second half, we're going to go to talk about what happens when we have regression instead of classification, right? This kind of analysis only works for classification, yeah? So we'll get started on the regression part, and then we'll wrap up on the regression next time. So just a bit more on this VC dimension, or the VC generalization bound. This is VC generalization bound, just what we have above, right? So if I just, copy this, well, I'll just write it. And dVC H plus 1 divided by delta, right? That's what we have. We can write one more step, yeah, just to see a bit clearly what this is. So because in general, we have big data, right? N is large. So we can just look at the scale. Well, let's look at the scaling of this thing, yeah? If I look at the scaling when N is large, then I can drop this plus 1, right? Just a constant, yeah? And then this log of N to the power becomes this dVC times log N, right? Yeah? And then this A and 4, I can drop them because we're just looking at scaling, right? So I'm going to use the big theta notation. I hope everyone knows the big theta, big O, small o notation, right? From your maybe algorithm or data structure class. I hope, right? Everyone have seen big theta before? Yeah? Just the scaling. Yeah, well, scaling. Just to be sure we are on the same page. Scaling. Yeah. So I can, this log of N to the DC power, again, this dVC times log N, right? So I can write the dVC out. Divided by N. I'm going to drop the 8 because only scaling matters. Log of N divided by delta, right? That's what we have. Yeah? Should be simple to see, right? Yeah. So if you have dVC, the VC dimension is finite, then this thing approaches E in of G, right? Because this is finite. As n goes to infinity, the big theta term goes to 0, right? So as n goes to infinity, right? Yeah. Okay. So in fact, you don't even need the dVC to be finite, right? The dVC can grow a little bit, can grow as n divided by log n, yeah? As long as less than n over log n scaling, then this thing will go to 0, yeah? So that's what this type of VC dimension analysis gives us. Yeah? Learning is quite possible, yeah, that the test error is same as your training error if you have enough data points. So you look at this, still the test data, the test error has two terms, right? It has to do with training error, and then that's the generalization error. So there is always this trade-off between the two, right? This is, well, I would say above here. This is called the generalization error, of course, as we have generalization error. Well, we denoted by delta G, right, last time, right? Yeah. So this is a generalization error for when the number of hypotheses is infinite, and then you can use this type of analysis. Yeah. So in general, we have trade-off between E in G and delta G. Yeah. So let's write it down. Trade-off between last week we discussed the trade-off between E in and delta G when M is finite. Yeah. Turns out that when M is infinite, you can still do the same trade-off analysis. You can draw a very simple, similar picture, only that here, instead of putting M there, your M is infinite, so it's better to put dVc, yeah, right? Vc dimension. And then the Vc dimension will represent the model complexity, right? How complex the model is. The higher is the Vc dimension, that means you have a more effective number of hypotheses, yeah? Therefore, the model is more complex. Yeah. So this is instead of M that we have seen before. Yeah. So when we have larger DVC, the model is more complex, and therefore the in-sample error is bigger or smaller? In-sample error. Smaller, because you have more hypotheses to fit the data, right? Yeah, the in-sample, oops, where does it go? The in-sample error goes down. Like that. This will be your E in of G. Yeah. The only problem now is that if DVC is large, and you look at the scaling above on top, right? The DVC is in the numerator, yeah? So you have more complexity, then your generalization error goes up. It goes up in square root of DVC, yeah? So it is, again, looks like this shape, like that. This is your delta G, right? And therefore, the test error, E out, is going to be something like a sum of those two. Yeah, that's roughly looks like this. E out of G. Yeah. And if you find the, let's say here is the lowest point, then this would be your DVC star, yeah? The optimal model complexity. So in other words, for example, you can have here, this DVC would be the linear model, yeah? Maybe over there is quadratic. Yeah, maybe over there, much higher DVC now, it is a neural network, let's say, yeah? All of these models would have infinite number of hypotheses, right? Yeah, but then you can still use the DVC, the VC dimension, as a metric for their complexity, yeah? And to indicate that the neural network, for example, is certainly more complex than the linear model. Make sense? Yeah? So this is one way to deal with having infinite M. Yeah? Then that way you can compare models that have infinite M, right? So of course, if you have DVC that's much bigger than DVC star, what happens? And if you use a model that's much less than the optimal DVC star, what does it mean? Yeah. If you choose a model H that is much, yeah? Yeah, that's called, we have a name for that. Overfitting, yeah, yeah. Exactly, yeah. The right-hand side will be overfitting, and then the left-hand side will be underfitting. Neither is desirable, right? So you have to choose the right model hypothesis, choose the right model complexity for the task at hand, yeah, so that your test error, E out, is minimized, right? That's the objective of learning, to minimize the test error, right? So the question is, what is the right model to choose? Yeah? Should I choose a linear model, a quadratic model, or a neural network, or whatever? Yeah. How do we know? Well, there's a general rule of thumb. The rule of thumb says that you want to the DVC star usually is around n divided by 10. Where n is the number of data points that you have. So the rule of thumb. Just no real justification for this. Just numerically people have found. Yeah, choose H. Choose the model, right? Choosing H basically means that should I use a linear model, should I use a quadratic model, and so on, right? Such that the VC dimension of the model that you choose should be approximately 1/10 of the number of data points that you have. In other words, if you have more data points, you can use a more complex model. Okay? That's the general rule of thumb. Well, your n usually is millions, right? That fraction is negligible, yeah? So it's roughly just divided by 10. It has to be a function of n because remember this bound on the test error is a function of both DVC and n, right? In fact, the ratio of those two. Basically, you want that ratio to be roughly 1/10, okay? That turns out to be roughly corresponding to the around this optimal. Now, not exact, right? Just rule of thumb, okay? Everyone okay? Everyone okay with what this means? Yeah? You can choose the model, right? Given the data set, I can choose to use a quadratic model. I can choose to use a neural network. Which one do you choose? Well, based on the DVC. That also means that you have to know what the DVCs are, the VC dimension of a linear model, and what is the VC dimension of a quadratic model, and so on, right? That's what this means. So let's take a look at some examples. We already seen last week, what is the VC dimension of a linear classifier, right? In RD, yeah? We have already said that this turns out to be d+1, okay? And we look at a simple example when d equals to 2, right? We list all of the possible numbers. And then we saw that the ghost function stops pretty much at 3. Yeah, n equals to 3. So therefore, the VC dimension is 3 when d equals to 2. Okay, so in general, this is true. Yeah, you have d-dimensional space. Then for linear classifier, the VC dimension is d+1. Okay, there's a very interesting proof in the textbook that uses some interesting linear algebra observation. Okay, I would highly recommend you to take a look at the proof, even though you are not responsible for that proof, say, in the final exam. Just good to take a look. It's one of the not an easy proof, yeah, but there's quite a few steps. But then it's one of the easiest proofs to derive the VC dimension of any learning model. Okay, it's an interesting proof. So yeah, if we have one more lecture, we can go through the proof. But as I now announce next week, let's skip one lecture, right, just so that we can have some fun, look at the solar eclipse, even though it does not involve this section. It would not be fair if this section also drag you to an evening class. So we all slack off for one lecture. And we're okay, because we have just enough time to finish everything that I want to cover. Yeah. Now, how about the quadratic model? Yeah? How do we derive the quadratic model's VC dimension? How do we know? So that when we have to choose whether we use a quadratic model, we have to know what is the VC dimension, right? So let's say for d equals to 2 as an example for now. Yeah? So that means your x vector is, say, in the augmented form would be x1, x2, like that, right? That's your original space, x vector. So to get the quadratic model, what do? We have to make a transformation to the z space. Yeah? To the z space. For quadratic transformation, what do we need to do? 1, what is this next one? x1, x2, square, right? x1, x2, right? x2 squared, right? This is the most complete transformation to the square polynomial, right? The second order polynomial, so quadratic form. Yeah? And then we do linear classification over this Z space. Now, the Z space, what is the dimension now? D equals to 5, of course, right? Yeah? Okay? So when you do linear classification in fixed 5-dimensional space, what is the VC dimension? Well, yeah, turns out that this quadratic model for d equal to 2 is the same as linear classification for d equal to 5. And therefore, we know that the VC dimension is 6. Okay? So this is equivalent to linear linear classification, I guess, not transformation. Classification for d equal to 5. Yeah. So therefore, we know that the VC dimension is equal to 5 plus 1 equal to 6. Yeah. So in general, you ask, well, what if I want to have a higher order nonlinear transformation, right? And then I also have general D. Okay. So case order polynomial. Then what would be the VC dimension of that? Yeah, for general nonlinear transformation, basically, right? Well, it turns out that you can easily figure this out. How many kind of terms you have, case order polynomial terms you have, right? So of course it is going to be k plus 1, I think. Yeah, choose D. Yeah, just binomial theorem, let's say. You can get that, right? So it's big O of k to the d's power. Yeah, roughly. K to the d's power is your VC dimension for nonlinear transformation. Yeah, clearly, right? Higher order nonlinear classifiers would have a higher VC dimension. Yeah, just by looking at that. Yeah. What about neural network? Yeah, our good friend, neural network. Let's just look at the binary case. You can extend this to multi-class as well. Same scaling anyways. So for neural network, turns out that it depends on what activation function we use. Okay? For most of the activation functions, we don't know. We don't know what is the VC dimension. Or it's infinity, some of them. Okay? But for the most basic ones, the sine function for activation and the regular sigmoid function for activation, we know that it is on the order of the number of edges or number of weights you have in the neural network. Okay, so with this simple activation or sigmoid, activation. Also, there's a mild requirement that the weights has to be quantized. But we always have to quantize the weights anyways in any computer, right? You always have to represent your numbers as ones and zeros. Yeah? So this is almost like a given anyways. In this case, the VC dimension is at most. We don't have a precise estimation for it, but we know big O of number of weights. Okay. So if you look at the linear classifier in d-dimensional space, d plus 1. D plus 1 is actually the number of weights, right, in the linear classifier. Yeah. So roughly, for linear classifiers, the number of weights. Yeah. So similarly, for the neural network, it's also the number of weights. Except that this is a big O, right? It can be any factor multiply number of weights instead of in the linear case, just d plus 1, right? This one can be 100 times the number of weights. Yeah, it depends on the structure of your neural network. Okay, so a bit more complex. Yes. Say again.
For the case order polynomial.
Yeah.
It's k plus 1 choose
D. Yeah. Yeah.
But for the quadratic, wouldn't that be like we choose 2, which is equal to 3?
Quadratic 3 choose 2. 3 choose 2 is 3. Yeah, that's a good point. There might be something wrong with this formula. Yeah, might have been a big O in front of that thing as well. There probably there's a big O in front of that, depending how you do the transformation. Yeah, I don't have. Yeah. That's a very good catch. Yeah, I'm not sure. Yeah. So the last one is the more important one. Yeah. If there are 6, then we have to have a d minus 1. No, 3 choose 2 is 3. You have to have how do I get 6? 3 choose? No, 3 choose 1 times 2. 4 choose 3? No. 4 choose 2. It's 4 times 2 divided by 2, right? I think 4 choose 2 will work. So might have been k plus 2 choose d, right? I'm not sure about that line, yeah? So yeah, take this as a, with a grain of sand, okay? But the last one is always, that one is the more important one, yeah. How about linear SVM? Turns out that, well, you can see that, well, because we have a margin, right? So certainly should do better than linear classifier, yeah? So in fact, one can show that this is upper bounded by d plus 1, yeah, the linear one, which is reasonable, right? And secondly, in the textbook, there's also an argument to say that, well, if the input is bounded, the data points are always bounded by R, then we have the VC dimension of gamma is upper bounded by the ceiling of R squared over gamma squared, where gamma is the margin, yeah, size of the margin. Okay, you don't have to remember this. Yeah? I'm not going to ask you questions about this exact form in the final exam. Yeah, even the case order polynomial one. Yeah? No one will ask you this to remember this. Okay, just the idea is just to look at the general form, how it behaves. Yeah. This one says that if you have a fatter margin, then the VC dimension is smaller. Right? So you have VC dimension smaller means that you have a less chance of overfitting, right? Yeah? Smaller VC dimension, less chance of overfitting. That's exactly what we expect. Yeah? Okay. So that's the general trend that people can show. Okay? So therefore, in general, SVM is less complex than a linear classifier, yeah, of the same order. So all of this is to pretty much conclude the generalization analysis for classification. Okay? As I said, you don't have to really remember these formulas, just to get a sense about the basic ideas. That's good enough. Yeah. The question then is, what about regression? Can we say something about the test error of regression? Yeah. Now here, remember in classification, we have this E-in and generalization error trade-off. Yeah, trade-off between E-in and delta G. Okay. Turns out that for regression, we don't have similar analysis anymore. Rather, we have another kind of trade-off called the bias variance trade-off. Okay. Today, we're going to spend about 20 minutes to get started on that, and then we'll continue next time. Okay? So I'm going to go to a new page, bias variance trade-off. regression. Any questions on the classification part before we jump there? Any questions at all? All right, so how do we set this up? Again, we have a training set. D, which has n data points, the same kind of notation that we have used forever, right? From the very beginning of the class, we've been using this notation. Yeah, and one thing that we only introduced recently is that we have this notion of a randomly selected training data set, right? Each data point is a independently chosen, so there's a distribution to choose the first point all the way to choosing the last point, like this, right? That's how we get the distribution of the data set D. And then we have an unknown target function. Which is y equals to f of x, of course. Yeah. The training error for any hypothesis G would be 1/n, the average training error per sample point, right? So each sample point we have to define a training error, right? And because this is regression, the common one would be square error. Like that, right? And then how about the test error? Again, test error would be for any given data point, we have an error, but then we don't know which data point we get, yeah? The data point for testing is randomly chosen. So again, we have to look at the expected value of that test error, right? So expectation g of x minus f of x squared. Yeah, and this expectation is over x, right? The choice of x that we have, that we are given for testing. And this x, of course, is chosen with the same distribution p as the training data points. Yeah? So that's our test error. Yeah, for regression. Nothing really changed, really, right? Only that this is a square error instead of a indicator function for the error. Yeah. So first thing to know is that the final hypothesis G is as a training, right? The final hypothesis is a function of the data set. Okay? So we want to explicitly indicate this fact so that we're going to give a new notation, a G of D, to represent the final hypothesis. Okay? G is a function of D. So it is random, right? Because the D is random. Come on. Not a question mark, but a reboot the pen. So we're going to give you a new symbol just to indicate this. So we're going to have the final hypothesis. We call it G of D like that. So in other words, our estimation, y hat, estimated label, would be G of D of x like that, right, for any x. And since this G of D is random, we can talk about its expected value. Yeah? So we have a mean hypothesis. Which is we denote by G bar of G like that. Yeah, well, let's say G bar of X is equal to, now it's going to be the expectation, but the expectation is taken over the random D, yeah, because the randomness of the final hypothesis comes from the randomness of the training data set D. Yeah. So this is going to be GD of X, like this. Yeah, so this is expectation over D. Which has a distribution of PD like that, right? Okay, where PD is just px1 times px2 times times pxn. Notice that this one is unknown, right? Because unknown in general, because we don't know the distribution of PD, right? Let's say unknown if PD is unknown, and that's our general assumption anyway, right? We don't know our data distribution. Yeah. Look at a quick example. A very kind of toy, very simple example. Well, first of all, D equal to 1, one-dimensional space, and we assume that the range of our data points is between -1 and 1. Okay, and then we have an unknown target function. So y is sine of pi of x, like that. Okay? It's there, but we don't know, right? The machine does not know anyway. The machine has to learn what this function is. And what is a training data set? Let's assume that n equal to 1. Okay, a very simple point, a very simple case, right? Not kind of a trivial toy example. So our data set contains only a single point, right? Let's represent a single point by UV like that. Yeah, where we assume that U is uniformly chosen between -1 and 1, yeah, within the space. Okay? This, and then of course V, because it's a true label, right? Clearly V has to be equal to sine of pi times U, yeah? U. Okay? Is the setup of this question, this problem clear for now? Yeah? You're given only one data point in the training set, okay? Just to make the calculation easy for us, yeah? Just one data point. Next time we're going to take a look at the case when you're given two data points, yeah? For now, that's just one. So hypotheses, well, since we only have very few data points, we have to consider very simple hypotheses, right? Remember, the hypothesis has to be simple compared with the data points you have, right? Simple enough. So let's say this is a set of just constant hypotheses. Yeah. In other words, the real dummy hypothesis, right? H of x is equal to c. Yeah, just some constant. You just have to choose the best constant for your hypothesis, right? So in that case, what do you think would be the best choice? Well, since you only have one data point to train this constant, clearly just say, I set it to V, right? Whatever label I observe from that one data point, I will set my hypothesis to that value. Is that right? So pictorially, suppose I have this, x between -1 and 1, right? And I have a sine function here, like that, right? And you're given one data point. Let's say the data point is right here. Suppose this is U that you're given. And the corresponding V, of course, the label is also given. Yeah, you're given V here. Yeah, this is the pointer you're given, right? You want to find the best estimate, but out of the H set that you have, right? It's a constant set. All of your hypothesis has to be constant. So therefore, you have no choice but to use this. This is your GD, right? Yeah. Right? This will be your final hypothesis in this very simple toy example. Everyone agrees? So in other words, well, what if I given another D, right? What if I'm given a U that's over here? And you're just drawing these points at random, right, for your training set that they give you, yeah? Then in that case, this is V. Yeah. If that's the case that you're given, this is the training data you're given, then your final hypothesis will be this one, right? So this will be your GD of X. Yeah? So I just wanted to illustrate that whatever final hypothesis you get depends on the training data set you have. Yeah? Whether it's the blue one or the red one, right? Okay? So therefore it's a random thing. Yeah? It's random depending on the training that you get. Yeah? What is the average hypothesis? Well, it's expected value over D of GD, right? By definition, this is the average hypothesis. Yeah? What is this equal to? Well, this D, the only one data point, right? Same as E of U, right? There's only one data point there. GD, I know is V equal to V, right? Always. Yeah? That's our choice. So therefore, this U of V is, I know, is a sine of pi of U. Yeah? What is this equal to? Well, this is a expected value of a function of random variable U, right? So you take the integration -1 to 1. What is the density of U? 1 over 2, right? Because U is uniform between -1 and 1. 1 over 2 is the density. And then you multiply pi times U, du, right? That's how you find the expected value of this function. Does this ring a bell? I hope everyone okay with this? EC302, right? Expected value of a function of random variable. Yeah, everyone comfortable with this? Now, what is the integration here? You can use your trigonometry formula to take the integration and so on, but you don't have to, right? You recognize the sine function is a anti-symmetric function around 0. So when you take a symmetrical integration like that, you always get 0, right? Simply 0. Yeah? So it turns out that the average, on average, your final hypothesis is just that x-axis, pretty much, yeah? 0, yeah, on average. So furthermore, we're going to define, we have to go to the bias and variance trade-off, right? So with this G bar, we can define the bias of a learning model. For some given x. Okay. We denote it by bias x, like that. Okay. It's simply how far away is this average hypothesis away from the true function, the true target function. So how far away? We look at distance, square distance, right? Because this is regression. Yeah? So this is, yes?
Sorry, so for finding the expectation value, how do we know that V is sine of pi U?
Oh, because V is a true label, right? V is given to you in the sign.
Yes, but we don't know the target. How do we
You know, the machine does not know. Machine does not know, but we know mathematically this is true. Yeah,
so
right?
we want
Remember this, yeah, as I said, this G bar is unknown, right? Unknown to the machine. Yeah? We're just doing analysis, what it can be. Yeah? Right? Yeah. this is for the, this is in general. The average is 0, but we don't know what training data point we get. Yeah. Yeah, this expected value is based on this hypothesis, right? The constant hypothesis. All of this analysis is based on this constant hypothesis. All of our it's just this line, right? The line, the x-axis. All of these lines, when you take the average, basically, right? All of these different lines, every time we have a different training data set, we get a different line, right? Yeah, all of this average of all these lines is just this 0 line. Yeah. Exactly. Yeah. Good. So and then we look at the bias. Yeah, how far away is this average away from the F, the true target? We also have the variance of a learning model given X. Yeah. So this we denote it by var of X like that. Simply the distance of GD. So every time that we are given a data set, we have a GD, right? How far away is this from the average G? The average of those GDs. Yeah, that's the variance, clearly, right? The random variable minus its own mean value. Yeah. Oops, I have to take the expected value. Otherwise, this will not be a variance. Yeah? We have to find the variance. So the variance of this. This variance, of course, is based on the randomness of D, so the subscript is D. Yeah. So this is the bias and variance of our learning model, given the data point X. So let's look at the example from before, the previous one. The same, continue. Yeah, what is the bias? I don't have to write X bar because it's one-dimensional. Yeah. Exactly. Yeah, it's a 0 for the mean, right? And then the true function is pi of X squared, right? So this is simply sine square pi of X, right? What is the variance? It's expected value. Again, the D is simply U, right? Our GD, the final hypothesis is always V, yeah? And the G bar is 0, yeah? Right? So this is E U of V squared, which is sine square of pi of U. Yeah? This is U. Right? And this would be, well, minus 1 to 1 half of sine squared pi of U. Yeah? How do you do that? Remember this trigonometry, right? Half. This is a half of 1 minus cosine 2 pi U, right? du. And I want to make it into a linear form because I know that for the cosine, when you integrate, this is actually 2 periods of that cosine. So you got 0. And therefore, everything remains. You get 1 over 2. Yeah. So now, what is the bias variance trade-off? Well, if I draw we want to find the actual difference. Let me copy this over. Let me get rid of the verb one.